Okay, so for this problem, we had to find the magnitude of the derivative of the velocity in the reference frame R. And how I did that was using this equation. Yeah. Yeah. So first I took the cross product between the angular velocity of H in frame R and cross product it with the velocity in frame H plus the derivative of the velocity in frame H. So t to the fifth in I hat direction plus t3 minus t to the sixth plus t to the third minus t to the fifth in the k direction. Okay, and then v dot h is equal to 3t squared in the I hat direction plus 2t in the j hat plus 1 in k. So adding these two together, I get 1.2, for like t equals to 1.2, we get 3.56, 3.95, and 0.24. And the magnitude of this comes out to be 5.3176, which is a little bit off from the actual answer, but I'm hoping it's due to a rounding error.
Yeah. Just we need to be careful about missing certain things. J hat over there. J hat over here. Okay.
Okay.
It might be better if you show the diagram instead of the, because I'll write down everything. Okay. So this problem has a lot going on in it, but it can be simplified to only 2 reference frames. And you can compare those 2 reference frames to turn everything into 1 reference frame, and then you can do all the math from there. So I'm going to draw what the 2 reference frames are. Yikes. Z, X, and Y. This is going to be reference frame A. And then in this reference frame, we have 2 angular velocities. We have one going this direction in the k hat direction. I'm going to call this W2 equals, and it's 1 radian per second. And then we have also an angular velocity along the y-axis. I'm going to call this W1, and that's 2t squared radians per second. So this is the first reference frame. And then the second reference frame occurs as a result of this rotation around z. So it's going to look like z is going to be the same. So z equals, and this new reference frame, I'm going to use the coordinate system with subscript 2. So this is z2, and it's going to have the unit vector k2. But it's equal to z because it's being rotated around that axis, but I'm just writing that for notation. And then you also have, due to the rotation around z, your x and y axes, they're still orthogonal, but they've been rotated some angle theta. And this is just, I'm just keeping this in reference frame B so we have it. This is the I hat direction from the previous reference frame. This is going to be the new axis, x2, in the I2 direction. And then this is going to be y2 in the j2 direction. And then obviously from the previous reference frame, this is the j hat direction. And this is theta, but we don't really care. But basically there is another angular velocity about the x2 coordinate system, or the x2 axis, like that. I'm going to call this W3, and this is 4t radians per second. So the goal is going to be to get all of reference frame B, everything in reference frame B to A, and for that we only really care about this, because this is the only angular velocity in this reference frame. So what we have is in A we have the angular velocity 1 in reference frame A is 2t squared j hat radians per second. And then we also have the second one is in the k hat direction of 1. So, and then in B, we have in reference frame B, omega 3 is 4t, and the I2 hat direction radians per second. So the goal is to find a relationship between I2 and ij and k. And so if we look at this, we can see that I2 is simply cosine of theta in the I hat direction and sine of theta in the j hat direction. So I'm going to write that down. I2 equals cosine of theta I hat plus sine of theta j hat. Oh, that's not right. Sine of theta j hat. But we have to figure out what theta is because it's not given. But we know that at time t equals 0, theta equals 0. And we know that it's rotating around this axis at 1 radian per second. So the problem is asking at time t equals pi over 2, what's the net angular velocity. So at time t equals pi over 2, theta equals pi over 2. So if you plug in pi over 2 for theta, this comes out to just be, do you have a new marker? This is dead. This just comes out to be I2 hat equals j hat, which means that we can express this in reference frame A as a omega 3 equals 4t in the j hat direction. So now everything is in reference frame A, so we can just say that the net angular momentum in A equals the sum of 1, 2, and 3 And we have two things in the j hat direction, one thing in the k hat direction, and nothing in the I hat direction. So this comes out to be 2t squared plus 4t in the j hat direction and 1 in the k hat direction. And then obviously you plug in pi over 2 into this. So the net angular velocity evaluated at t equals pi over 2 comes out to be 11.218 j hat plus 1 k hat. This is all radians per second. And then if you take the magnitude, you get magnitude of A W net equals 11.2625 radians per second.
Okay, so my problem was, it said that it's similar to the previous problem. However, I took a slightly different approach. Okay, so we have a couple frames of reference. We have G, which I'm going to draw like this. We have B, which is like this. And then we have A, which is slightly at an angle. Okay, so let's start with G. We have x1 in the I1 direction. We have y1 in the j1 direction. And then we have z1 in the k1 direction. So in this reference frame G, the only thing that is moving is wz right here, or omega z right here. So we have, I'll draw this, omega z. Okay, B, the B reference frame is after it's kind of rotated a bit. So this is basically like the original axes, x and y axes. The z is fixed. The z-axis is fixed, so I'm going to call this z2 is equal to z1. We have, so this is x1 for reference, and this is y1 for reference. It's rotated, I'm going to call this an angle beta. And we get x2 in the I2 hat direction, and y2 in the j2 hat direction. This will be in the K2 is equal to K1 hat. And in the B reference frame, the only thing that's moving is the omega x from the A beam. Okay, now in the A direction, we're going to fix x2 and I2. So we're going to call this x3 is equal to x2. So I3 hat is equal to I2 hat. For reference, this was y2, and I'm going to call this theta. For reference, this was z2, and this is also at an angle theta. So this is z3 in the K3 hat. This is y3 in the J3 hat. Okay, so we finally established our reference frames, our angles, and then included, oh, one more thing. The only thing that's rotating in the A is the C, which is going in the Y direction. So like that. So omega y. So yeah, we established the rotations, we established the frames of reference, and the different angles. Okay, next we have to find omega c with respect to g. So c is going to be this body right here. We have to find it with respect to the ground using all three angular rotations. So how you do that is you break it up into parts. You do omega c a plus omega a b plus omega b g. So c with respect to a with respect to b with respect to g. Now, okay, we look at c with respect to a, right? So c with respect to a is the most complicated one. What we want in the end is in terms of this coordinate system right here, x2, y2, and z2. So we're going to look at the angle between y2 and z2, this theta right here, and we're gonna break apart this angular rotation into its components in the y2 and z2 direction. In that you get omega y cosine theta in the j2 hat plus omega y sine theta in the k2 hat. Okay, now we want omega AB. So omega AB is just going to be this omega x direction because that's the only thing moving in that frame of reference, which is this beam right here. So that's pretty simple. We just have omega x in the x2 direction, so I2 hat. And then last, we need omega b with respect to g, and this is going to be that omega z right here. Omega z in the, it is in the k1 direction, but since we established k2 is equal to k1 here, we can call this in the k2 hat direction. Okay, now we have our full equation. We can simplify this to okay, we have this equation. Now, only thing left is to solve for theta. Theta is pretty simple. Theta is equal to the angular rotation of this axis and how much time it does that. So we have the time, 3.9 seconds. We have the rotation, which is going to be, what is it? Sorry, 7 radians per second. Radians per second times 3.9, which is equal to 23.4 radians. Okay, now if you plug, we have Wx is equal to 7, Wy is equal to 6, Wz is equal to 6, and then we now have theta. This is all in radians per second. Now if you plug everything in, do the algebra, you get oh, one more thing, forgot to mention. We only want the k-hat direction, and we want it in terms of B2. The only thing different from G and B is this angle beta here, but since we want it in x2, y2, z2, we're not going to care about beta. So if you just do the k-hat component here, plug in all these variables, then you get 10.69 radians per second.
Brilliant, good theta. I'm not sure if you already mentioned, but when you're getting theta,
Yes.
You should also mention a theta naught and use the initial condition which was mentioned there. the drawing that at t equal to 0, the axis orientation.
Ah, okay.
Sorry, the axis is parallel to y at t equal to
Yeah.
0. So it's because of that that you can just stay with 23.4, otherwise
Yeah.
add an addition later on.
Right. So if it was at like some angle, then we'd have to add that angle in. Okay. Makes sense.
Okay, so for this question, you have two angular velocity vectors shown in the table as function of time, and the orthogonal unit vectors are fixed in the direction of frame B, so these are different frames of reference. And we have to find the magnitude of the angular acceleration of c in A at time t equals 1.1 second. So first, before I do it on the board here, we're just going to use the equation that relates the angular acceleration from one frame of reference to another. And for that, I'll write that equation down here. So we've got okay, so this is the equation here, and we are given the angular velocity, so I'll just write those here. So sine ti plus cosine tj plus 7tk. So and then C and B, they've also given 4t squared I plus 2tj plus 5k. And then to get angular acceleration of C in A, we do need these two components as well. And since we're given the angular velocities at that exact frame of reference, we can just take the derivative. So let's do that right here. So we have cosine t I minus sine tj plus 7k. And then for C in B, we have 8ti.
You should also mention which frame you're taking the derivative.
Okay. Yeah. So we're doing it's B in A with respect to A. Yeah. So for angular,
Remember that I hat, j hat, and k hat are fixed.
they're in
only
frame B.
base.
Yeah. They're fixed in frame B. So this is also in frame B. So we have 8ti plus 2j plus 0k. And so now we have everything we need to get the angular acceleration. So we have, first I'll do the cross product over here. And if you do the cross product, we get 5 cosine t minus 14t squared. So we have that. And then, so now so this would be this term, and then we can add it over. So have CB here. So if we look at the I components, we have ATI plus cos TI plus 5 cosine t minus 14 squared. So you'll get 8t plus 6 cosine t minus 14t squared. Then J, we have 2 minus sine t minus 5 sine t plus 28t cubed. So 2 minus 6 sine t plus 28t cubed. And then we have 0k plus 7k plus 2t sine t minus 4t squared cosine t. So we can just make that a 7 plus 2t sine t minus 4t squared. So that's our angular acceleration vector of c with a, but it's at c and a, but it's with in terms of t. But they want it at t equals 1.1 seconds, so we'll just do angular acceleration of c with a. C and a plug in t equals 1.1 seconds. If you plug that in for I, j, and k, you get negative 5.42 I plus 33.92 j plus 6.77 k. And they want the magnitude, so I just take the magnitude. And you get 35.01 radians per second squared. Yeah. If it wasn't in frame B, we would have to do 2 conversions. We'd have to convert with B and then convert after.
They keep dying. So.
Okay.
Here you go. Oh. Okay. So I'm not even going to attempt to draw that, but I'm going to do something interesting with the reference frames, or the way I like notate them. So this is y, j hat, z, k hat, and x, I hat. And then I'm also going to draw the second reference frame. I don't want to waste space, so it'll be a little bit confusing, but and then this is K2 hat, I guess Z2. This is going to be Y2, J2 hat. And then this is going to be X2, which is I2 hat. And then I'm just going to say that A is the dotted one and B is the solid line. And we want everything in reference frame A. There's 4 different components to both systems. So we have omega 1, about x or x2, which equals 2.9 radians per second. And then we also have omega dot 1, which is negative 1.2 radians per second, squared, sorry. And then about the k2 direction, we also have two rotations. One is velocity, one is acceleration. So we have omega 2, this one, is equal to 2.2 radians per second. And then omega 2 dot is equal to 2.1 radians per second as well. Okay, it's a little bit messy, but we'll get through it. So we want the net angular, the goal is to find the angular acceleration, but first we're gonna have to find the net angular velocity, and then we can take the time derivative in reference frame A to find the net angular acceleration in reference frame A. So first, to find the net angular velocity in reference frame A, so obviously we have I hat 1 is equal to I hat 2, and we have both, we just have this angular velocity. So equals A W1 in the I hat direction. And then we need to express W2, which is in the K2 direction, in terms of Y, like J hat, K hat, and I hat. So just by trigonometry, it's going to equal, we're going to have minus W2, or actually I don't need this right now, W2 sine of theta in the J hat, and then plus W2 sine of, cosine theta in the K hat direction. So that's the net angular velocity in reference frame A. Now, we can differentiate with respect to the reference frame A. So that's just going to be a d over dt of W1. I have no space actually over here. I'm going to go down. Okay, so what's the time derivative of W1? Well, it's just W1 dot. That's really simple. In the I hat direction still. Now, it gets a little bit interesting here because theta is not a constant. We're given at a specific time what its value is, but it's changing. It's literally this value here, W1 dot. Or sorry, W1. That's going to be theta dot. It's changed with respect to time, so we're going to have to do the product rule. So let's look at the j hat component. It would be, we have W2, first taking the derivative of W2, W2 dot sine of theta. And then we would add, because, huh?
The Greeks wouldn't be happy
Oh.
to keep calling it W.
Yeah, sorry, I'll call it omega. Omega 2 a dot sine of theta, and then by the product rule, it's omega 2 cosine of theta times, we have to do the chain rule now, times theta dot in the j hat direction. And then let's do the same thing for the k hat direction. So once again, it's going to be omega 2 dot cosine theta. And then by the product rule, it's omega 2 times negative sine of theta times theta dot again. And that's in the k hat direction. So I'm just going to write all the variables out once again so we know what we have. So we have omega 1 dot, negative 1.2 radians per second. Omega 2 dot is 2.1 radians per second. So we've got omega 1 dot, we've got omega 2 dot. We need theta. Theta is 30 degrees. We have theta. We need omega 2. Omega 2 is 2.2 radians per second. And the last value we need is theta dot, which equals omega 1, which equals to negative 2.9 radians per second. I actually, I messed up here. This is supposed to be negative because if you do the right-hand rule, it's going that direction. So you would plug all of these into this equation, and it comes out to A, in reference frame A, the time derivative of the angular velocity can just be rewritten as the angular acceleration, and it equals negative 1.2 I-hat direction plus 4.475 in the j-hat direction plus 5.008 in the k-hat direction. This is all in radians per second squared. And then you just take the magnitude, and it comes out to 6.82307 radians per second squared. Yeah.
So for this one, it's the same diagram, except now we've added a stone on one of the sides, and we're trying to find the velocity of that stone with respect to the ground. But we can't do that directly. We have to take into account the reference frames. So they gave us the velocity of the stone with respect to the seesaw, which is reference frame B. And they also gave us that the seesaw is turning at an angular velocity omega h, which is 2.4 radians per second, which I'll write here. And then they gave us also the omega v, which is the angular velocity of the merry-go-round with respect to ground. So we have to do stone with respect to board, plus board with respect to merry-go-round, plus merry-go-round with respect to ground to get the total stone with respect to ground. So let's, and they also gave us that this is all happening at theta equals 0 degrees. So that would, these are our JK vectors right here. So they also gave us that the stone is 1.6 feet away from the girl at this instant, which will help us find the velocities from because the linear velocity is equal to omega r, and we can use the r of the stone, and we know that both children are 5 feet away from the fulcrum of the board. So the radius of the board is 5, but for the stone it would be 5 minus 1.6. So I'll write out my work here. So velocity of the stone with respect to ground is velocity of the stone with respect to the board plus the velocity of the board with respect to the merry-go-round plus the velocity of the merry-go-round with respect to the ground. So velocity of the board with respect to the seesaw, they gave we use omega h for this. So omega h times r for the stone, and that's 2.4 radians per second times 5 minus 1.6 feet. And that equals 8.16 in the I-hat direction over here. So 1.6 I hat direction feet per second. And then for v of the merry-go-round with respect to the ground, we have omega v times r of the stone equals 2.6 radians per second times 5 minus 1.6 feet and equals 8.84. And this would be, we have that in the k hat direction. So and now we already we're given v of the stone with respect to the board, so we can add these three vectors, and we have vpg equals 8.16 I hat plus, minus 3.8 j plus 8.84 k, and that's feet per second. And then we'll take the magnitude, because that's what it asked for, square root (12.6163 feet per second.
Just I would like you to be a little careful. We can never talk about the velocity of a body, and we can't talk about the angular velocity of a point. Okay? So when you say velocity of, this is okay because it's a point, stone can be treated as a point. When you're talking of the board, it's a particular point on the board.
Right, sorry,
So
I should have
similarly,
specified
yeah.
it's the stone that's on the
Exactly,
board
right.
with respect to the seesaw. So
the
same thing,
instantaneous
stone.
position of the stone on the board. So whatever that point on the board is, we are referring to that
Point.
So
Yeah.
we could use a different symbol like a B bar or something like that. So
Yeah.
the same thing with the J as well over here.
Yeah, that's true.
The second J is fine. Yeah, and the second G is fine. Second B is
Yeah.
fine because that's with respect to a rigid body. But the first one is always a point.
Yeah. Sorry. I keep forgetting. Yes.
Okay, so for this question, it asks to find the magnitude of the angular velocity. of the spinning top relative to the Earth's reference frame. So we are given the angular velocity of the spacecraft with respect to the Earth, and then we are given the angular velocity of the top with respect to the spacecraft. So in order to get the angular velocity of the, in order to get the angular velocity, it gave out. Okay. In order to get the angular velocity of the top with respect to the Earth, we have to do the cross. Wait, no. Oh. We just add the two angular velocities together. So this is T E is equal to so the vector that we get is 7.4 in the I direction, 1.09 in the J direction, and then 0.51 in the K direction. And then the question asks for the magnitude, so we have to take the magnitude of the angular velocity of the top with respect to the Earth, which gives us 7.4972.
Rather than IJ and K, you should mention V1, V2, and V3.
Oh.
And that's fixed in the spacecraft reference frame. That's why you're able to add both, because both are in the same frame.
Okay.
So when you write, for example, the actual values, this doesn't take into account that it's along the V frame. So typically we mention a B over here, that this is along V1, V2, V3. Okay? Because now we're talking about the top with respect to the Earth. So unless we mention B, this would not be valid. Yeah?
Okay.
But anyway, since you're interested in the magnitude, didn't matter which frame you were in.
Okay.
Okay, so this problem was pretty similar to the last one, except we have an angular acceleration of that top now. Okay, so the formula for this is we basically want the angular acceleration of the spinning top in the Earth reference frame. We're given angular acceleration of the top in the spacecraft. We're given both the velocities of the spacecraft and then the top with respect to the spacecraft. So we have all that we need to compute this. We have alpha b with respect to a is equal to alpha c with respect to a plus alpha b with respect to c plus omega c with respect to a cross omega b with respect to c. Okay, so now basically I'm going to say the top to the Earth is equal to spacecraft to the Earth plus top to the spacecraft plus the spacecraft to the Earth cross with the top to the spacecraft. So that's just the, yeah, forgot that. Okay, so the spacecraft with respect to the Earth is given to be 0. The top with respect to the spacecraft is given to be, and they use B1, B2, B3 hats just for the sake of avoiding confusion. I'm just going to use I, J, K. They stand for the same thing. So we have 0.06 I hat plus 0.11 J hat plus 0.26 K hat. Okay, now that's that. Then we have plus omega C with respect to A, which is spacecraft with respect to Earth, is going to be 1.1 I hat plus 0.82 J hat plus 0.35 K hat. And then the top with respect to the spacecraft angular velocity is given to be 8.3 I hat plus 0.12 J hat plus 0.17, right? Yeah, 17 K hat. Okay, so this is given us to be in radians per second squared, and all of this is in radians per second. Okay, now we compute the cross product. This cross product gives us to be 0.097 I hat plus 2.718 J hat plus, plus negative 6.674 K hat. You do the cross product, you get radians per second squared. Okay, now we basically just add these up together. You get 0.157 I hat plus 2.828 J hat plus negative 6.414 K hat. And that's after adding this, which is the cross product, with this original angular acceleration. Okay, now we basically have it in I hat, J hat, K hat. This is going to be alpha B with respect to A, which is top with respect to Earth, which is what we want. We also want the magnitude of that, so what we do is take the magnitude, and after doing the math, you get 7.0115. Wow. Radians per second squared.
And we just wanted to save time writing, but once you have this as a cross product, this is also radian per second squared, right?
Yes.
Crossing these
Yeah.
two, otherwise you can't be adding this.
Yeah. Okay, I also did the next problem. Next problem was also pretty simple. So what we want is the pitch angular velocity q, in radians per second. So we looked at this formula in class. Q is equal to phi dot cosine theta sine phi plus, this is psi dot cosine theta sine phi plus theta dot cosine of theta. Okay, pretty simple. We are, huh? Cosine of theta. Yeah.
I thought it was phi.
Is it?
I use phi in my problem.
Give me just 1 second. I should have the formula here somewhere. Cosine of phi, you are correct. Calculation still worked out. I think I just wrote it wrong in my notebook.
It's because theta dot is 0, so it doesn't matter anyways.
Yeah. Okay, so psi dot is equal to 0.14 radians per second. Phi dot is equal to 0. Theta dot is equal to 0. Phi is equal to 22 degrees. And then theta is equal to 2 degrees. Okay, we have some difference in units, but it doesn't matter because we're not actually taking the sine or cosine of this. Anyway, if you plug everything in and use the correct calculator functions for degrees or radians, like I did not on the first try, you get 0.0524 radians per second.
So they gave us the angular rates for roll, pitch, and yaw at an instant in time. The orientation of the aircraft is given by their phi, theta, and psi that they've given. So we have to find the yaw angular velocity, r. So there's a formula for this. So we have r. We're talking about yaw here. We're talking about yaw here. So that's phi minus theta dot sine. So this is the yaw angular velocity. And I'll write what we're given. So psi dot 0 radians per second, theta dot 0.17 radians per second, and phi minus 12 degrees. Notice I put degrees here because, so we have to have everything in the same unit, so I have to convert this. It's 12 pi over 180 radians. And I did not include like phi by itself because that wasn't on here. And also, since psi dot is 0, we can just cancel this term out. So we have r equals, from this one we have 0, I'll just write it. So we have 0, but then here we have theta dot 0.17 radians per second, sine 12 pi over 180 radians. And so if we evaluate that expression, we have negative 0.0353 radians per second. Yeah.
Okay. This problem is kind of a combination of the previous ones plus a little bit more. So we have one of the equations we learned last class is that in reference frame, I'm not gonna draw the reference frame, but I'm going to say that we have some reference frame A with respective unit vectors A1 hat, A2 hat, and A3 hat. Is there a better marker? Cool. And so with this established, we have in reference frame A, the angular velocity is equal to P in the A1 hat direction plus Q, the A2 hat direction, plus R, the A3 hat direction. And we don't want angular velocity, we want angular acceleration. So very simply, if you take the time derivative in reference frame A of the angular velocity, you'll get P dot plus Q dot plus R dot. And obviously, this also equals the angular acceleration in reference frame A. So let's write down what we have. So recall that we have, phi dot equals 0.15 radians per second. Theta dot equals 0.13 radians per second. And z dot, or psi dot, equals 0 radians per second. So P, Q, and R, I'm going to look at them individually, and I'm going to evaluate them before taking the derivative, but only in a very specific manner. So P equals negative psi dot sine of theta plus phi dot. And we have that psi dot is 0, so this term will go to 0. And we have that phi is 0.15, so this comes out to 0.15 radians per second. Now if we look at Q, we have z dot cosine of theta, sine of theta, sine of phi, plus theta dot cosine of phi. Once again, this term will go to 0 because psi dot is 0. Plus, and then theta dot is 0.13. But we also have phi, but we don't put it in yet because we have the instantaneous phi, but it's also changing. So whenever we differentiate, it's going to change. So this is going to be 0.13 cosine of phi radians per second. So that's what we care about. And then if we look at R, psi dot cosine of theta, cosine of phi, minus theta dot sine of phi. Once again, whole first term goes to 0. The second term, negative theta dot is negative 0.13. And then sine of phi, is it sine of phi? Yeah, sine of phi. And then radians per second. And for the same reason, we don't plug in our value of phi yet because it's changing. So now we're going to take the time derivative of these things. So we also have, I'm going to write down the actual angular values. We have phi is 18 degrees, theta is 12 degrees, and psi is 133 degrees, which we don't actually care about. So in reference frame A, if we take the time derivative of P, we will get the time derivative of a constant 0.15 radians per second, which is 0, just P dot. Okay, cool. Now do the same for Q and R. Of Q, this will be 0.13 cosine of phi. And then, because this is changing, we're going to have to do the chain rule. So this is derivative of cosine of theta is negative sine, so negative 0.13 sine of phi times phi dot. And if you plug in all these values, this comes out to negative 0.00603 radians per second squared. And this is Q dot. And then doing the same for R. this is time derivative of negative 0.13 sine of phi, which is negative 0.13 cosine of phi. Chain rule, phi dot. Plug everything in. This comes out to negative 0.0185 radians per second squared. And so that's r dot. And I guess this technically should have also been radians per second squared. So yeah, now we have p dot, q dot, and r dot, but p dot is 0. So the whole angular acceleration in reference frame A is negative 0.00603, the A2 hat direction, minus 0.0185, the A3 hat direction, radians per second squared. And then if you take the magnitude of that, magnitude of angular acceleration in reference frame A is 0.0195 radians per second squared.
Glad Chris pointed out a couple of times that size changing, don't substitute for it. That's a common mistake a lot of the students do.
Yeah.
Substitute a little earlier than necessary. So make sure that if certain things are changing and you need to take the derivatives especially.
Well, yeah, like if you substituted in here, you would get a constant, and then when you take the derivative, you get 0 again. So it's because it's changing, you don't substitute it in.
Okay, so for this problem, we have to calculate the z component of the vector in the Earth's reference frame. So basically, they're asked. Okay, so and then they give us the angle of phi, theta, and phi, and the magnitude of the length of the wing from the center. Yeah, the center of mass of the aircraft to like a point on the wing. So these angles are giving you like the orientation of the wing at that moment. And because it's kind of like hard to like draw a three-dimensional line, I'm just gonna like write like their changes in like axis directions, if that makes sense. So this one is 13 degrees. We're just going to call this this one is 17 degrees. Okay, so it gives you like the magnitude of the length of the wing in like the y direction, which is 6.3 meters. So in order to get like the z component, we have to multiply 6.3 times sine of this angle by the cosine of this angle. And this gives you 1.3553.
Just be careful when you mark the angles, because remember in the last class we talked about the 3-2-1 system. So the second angle is actually with respect to an intermediate frame. So be careful when you mark it, because and the reason why this works is because you're multiplying the component with another cos. So you're essentially taking the component off a component.
Okay.